surface integral x squared plus y squared plus z squared ds. S is the part of the cylinder x squared plus y squared equals 4 between those horizontal planes z equals 0 and z equals 3. Parameterize the cylinder and use the parametric form of ds. So really what we just did is a good lead-in to working through this problem. This is another one of those you're not going to see, although if you can do the problem I just did, you can do this one. So you've got to figure out how to parameterize it, and that is something you should be able to do for the final. So it's worth talking about, at least working towards how to set it up. So if you want to parameterize this cylinder, well, you got to use basically the same trick you learned in your last class as to how to parameterize a circle and then put in a third component for your vector valued function, right? So parametric equation wise, it's a circle radius 2, right, in the xy plane. How would you parameterize that? What would x equal? What would y equal? So yeah, I like what you said, r cosine theta, but r is a specific value here, 2. 2 cosine theta is the usual parameterization for x, and then y equals 2 sine theta. Theta is going to have to run from 0 to 2 pi. Okay, usually we use u and v here, so I'll be trying to be consistent with that. Does it matter? No, although you do want them both to be u for the circle. I mean, it only takes one parameter to describe a circle because it's a one-dimensional object, right? Think about it. Yeah, we graph it in R2, the xy plane, but any curve in R2 is a one-dimensional object. So it should take one parameter to describe any curve. And that can help you not make mistakes and call that second one 2 sine of v or something like that. And then to make it a cylinder, you need a third. So this is like the generating curve, right? That's a circle, the parametric equations of a circle, x and y. So to make it a cylinder in space, you need a third parametric equation, z equals, how do you raise up or lower that circle? You just let z vary and let it be any real number, right? Yeah. So that's what's going to be your other parameter, v. And so you can say that u has bounds 0 to 2 pi, and normally v is any real number if you want to describe the whole cylinder. But if you think about it, you can't integrate over a whole cylinder. It's got to be a bounded surface, right? The bounds are given in the problem. Z is v, so it runs from 0 to 3. And if you weren't given those bounds, you couldn't do this problem. Because normally when you parameterize a cylinder, that cylinder goes up, and if it's a vertical cylinder, it goes up forever, it goes down forever. So now you can imagine what it looks like, what you're integrating over, right? Oh, it's a cylinder, kind of a Pepsi can shaped cylinder from a height of 0 to a height of 3. You're finding that surface area, right? Well, okay, no, it's not a surface area anymore, right? I mean, if that's all you were doing, you could use there's a known formula for the surface area of a cylinder, right? You could use that if you can remember what it is. But this is actually a surface integral because the integrand's not 1 anymore, right? So I think, Joshua, your question was then something about z? Yeah. Anytime it's almost, once you get used to it, it's almost more straightforward. I don't want to say easier because it's not. It's almost more straightforward to do things in parametric coordinates because your x, y, and z are in terms of the parameterization. So if you're going to actually evaluate this, let's do that. Let's take it that far. It's the integral. Okay, what's x? 2 cosine squared u. Now, I'm not sure I want to plug those in, though, because when you take x squared plus y squared, what are you going to end up with? Aren't you just going to get 4? Yeah. So this first part, I mean, if you didn't see that, eventually you would, because you'd see the identity staring you in the face if you plug it in directly, and that would work. If you factor out the 4 after you square it, you'd have cosine squared u plus sine squared u left in parentheses, and that's 1. Or just call it 4 and be done with that part of it, right? And then the z is v, isn't it? So 4 plus v squared. And then we could do dv du. And then what does v run from? 0 to 3. What does u run from? 0 to 2 pi. And then what am I forgetting? Yeah, remember ds is equal to magnitude RU cross RV. And then in this case, we're going with dv du for our dA. I'm going to let you verify that magnitude RU cross RV is equal to 2. So that as long as we put in a factor of 2 in here, we're going to be good to go. And there's your setup.